Okay, so now is the time for the last, but as usual, not the least, presentation. So I will comment about the programming of flexible robots, what we have been doing in the project, also in collaboration with the team of Mathieu at CEA. And yes, now it's working perfect. So let's start and try to fit to the time. So the context, it's quite simple. We have a system that starts to be getting more and more complex. Two anthropomorphic arms with embedded force sensor, two dexterous grippers that Mathieu just presented, a vision sensor that is located as of today in the middle here. And we want to have this connected with the digital twin to collect the motion and the location of the different elements perceived. We want also to be connected with the reasoning system. So a lot of element to control, a lot of interfaces to handle, and it's not that obvious how a non-specialist can handle of this. And so what we are interested in is bridging, making a bridge in between the operator that not necessarily is a roboticist specialist and this complex platform. And to do so, I'm going to present different level of providing some support at 3 levels. I will start at the action representation, the skill mechanism that I briefly mentioned in the first session. Then we will go, I guess, toward the programming interface that is proposed to the operator. And then we will also look at the low-level control that may not be of interest for the end user, but is quite important for the integrators and to show how we propose to implement a complex behavior with our system. All right. So as I said, to represent the action and also to simplify the execution, we are using a skill framework that consists in basically to abstract each of the capability of the system. So that any operation that can be conducted by the robot, that can be detect an object, grasp an object, move towards an object, insert the canister, is represented as a skill. So that the process will be then a collection of skills to be executed progressively. The advantage of making an abstraction like this is that we can easily agree such interface with different providers or partners, and it will definitely, and it did, facilitate the integration, the deployment, and the execution of the process. Because for the system at the end, assuming that we have a bank of skill, a set of functionalities that can conduct the robot, then a process is just a set of skills that we want to execute one after the other. So that for the skill engine, it will just progressively give the hands to the first one up to the next one without having to enter into the details of each functionality. It kind of simplified the execution of the system and also all the previous step of deployment and integration. And so this is something that we have been using yet from the beginning until the end of the project, and we are still using it. And it's also interesting to have this type of functionality because it simplified the extension. As we have a common pattern for each component, then we can easily extend it. And that's what we did to communicate and have a systematic tracing of the operation, because we went from a skill model toward a traceable skill model. So that's in the model, we enforce to collect the input of each skill and the output of each component, and then this information is directly shared with the tracer component and provided inside the audit trail. And this is super easy to implement as we are using a framework, a common model for each component, so we can extend the model with this type of information. And we also did something similar to incorporate some verification means, assuming that we have a hierarchical structure of the process. If we assume that the last operation to conduct is a verification, this information can be provided to the tracer and automatically also incorporated into the traces collected with the process. And we also did something similar to connect with the reasoning framework that was presented by Franklin. We have a direct communication in between the skill management and the reasoning framework so that we can automatically inform the reasoning framework about the action that is being executed and when it starts, and so that we can make sure that this action can be executed as explained Franklin, and then we can provide also all that semantic and temporal information to create the names that was also mentioned by Franklin before. So having this type of framework that supervise, I would say, or organize all the execution of the action is super practical for extending and provide and added some additional functionalities on the top of that and to distribute it to the complete system later on. And as the question was raised before, so all this mechanism is implemented into ROS, and the advantage is that it also facilitates the deployment of the solution. So as I already mentioned, we have been using different type of platform. Here at Tecnalia, we have UR5s. We have been using UR5. Then at Aztec, we were using UR10 with B-digital grippers at the beginning, with advanced dexterous gripper later on in the project. But we were still maintaining the same structure, the same main process, I would say, because somehow at the level of the process execution, we are a bit agnostic to the model of the platform that we are using inside the structure. So it was super practical to use this type of representation, and also is the reuse of the different skills that we implement from one process to another. So it was a very good choice that was done at the beginning of the project. Looking now at the programming interface that I briefly mentioned also in the first session. So if we assume that we are going to rely only on the pre-existing bank of skills, then we can either program the system using a graphical interface, or as I will illustrate it, using kinesthetic teaching. But also there are some functionalities that enables to learn new skills, so to extend the bank of skill or to adapt better the bank of skill to a given situation that I will briefly also mention later. So regarding the basic model that is using a graphical interface, so CER has been working on this aspect. Will not provide videos on that, but what is interesting to mention there is that we were using the fact that each of the skill used were grounded into the ontology, and this enables to provide a list of skills that are suitable depending on the current state of the virtual world environment, right? So if we virtually execute the different skills that have been collected into the process, then we can select a skill, we can filter the list of skills according to the one that makes sense in that situation. So that typically, if we have detected a canister, in that case, then the next action that could be related to that is operation that look at grasping this canister. And then if we incorporate the grasp canister, then we can assume that the canister is inside the gripper, so we should not propose to the user an operation that consists in grasping another object, because we cannot do it within the current state of the process. So CA has been using this semantic information associated to the different skills to facilitate and filter and improve the intuitiveness of the graphical interface for selecting the set of skills. But they have been also working on getting rid of the interface and directly using kinesthetic teaching to make a demonstration of a process and let the system recognize from the bank of skill which is the set of skills that is used by the human to perform the operation, so that then we can execute it automatically. And that's what you can see in this video. So first initialization to define what is inside the environment, but then our colleagues, Raphael from CEA, is manually moving the robotic platform in between the different items, moving one object to his site and so on and so forth. And while the Raphael is doing this operation, the system is monitoring the signal, the position of the object, the position of the different items, the status of the gripper as well, and that information enable to segment the sequence and also to define some evolution of the environment. And that information is then used to automatically, based on the semantic information associated to the different skills, to automatically recognize the different skills that have been used by Raphael in that process, and to generate, as you can see here, a list of action that could be conducted by the robotic system to reproduce the same operation. And that's what we are going to see in a few seconds. So here the interest is that by only moving the system, we can show to the robot the operation, and the robot is able to recognize what was done. So of course that makes sense when the operator can be in the same environment as the robot, which is usually not a problem with such collaborative robots that are designed to work in the vicinity of human, but might be in some cases problematic if the deployed environment does not permit to have a human inside. But here, as you can see, the robot is reproducing what was done by the human automatically on its own, according to the automatic recognition of the skills that have been employed. But here we stick to a bank of skills that are predefined and provided. So what if we want to learn a new motion? What if we want to extend the bank of robot motion the system can handle? So we have been working at Tecnalia on that, using in that case teleoperation, so that here my colleague Miguel is teleoperating the robot, showing to the system a new behavior, that is to position the bottle inside the holder. And in the meantime, the system is learning, looking at the trajectory of motion of the robotic arm and applying a model, a dynamic movement primitives, on the top of it, that enables later on to reproduce the behavior that have been observed automatically by its own. So here the robot is replicating the motion that has been learned and able to perform the motion while adapting, having the possibility to adapt the starting and ending points according to the real situation. Another way to learn new skills is eventually to fine-tune an existing skill according to the situation. So in that case, Miguel again will be showcasing how we can open the sterility kit, and we assume we already have such a skill in the bank of skills. But what we are looking at during the demonstration is, well, parameters that will be used to fine-tune this generic controller that we have. And in that case, we are looking at the linear velocity information and the interaction forces in between the gripper and the lid. And then based on that information collected, the system is able to reproduce the behavior, adapting the motion direction to what was perceived with the human operator, and also take into account the appropriate forces required to pull that layer out of the kit. So these are different modalities that can be used also to extend the bank of skills and to provide to the system new motion capabilities. Briefly looking at now the low-level control, where we have been also contributing. So here the objective is to see how we can, well, define control laws to move the robot from A to B according to some constraints. And to do so, though, we're also using the ROS middleware. So that's famous programming environment for robotic platform. What is interesting is that this system provides an abstraction of the robot you want to control, and also provide the generic controller management so that it's quite, I mean, as it is kind of standardized, you have a bit more robustness in the implementation and confidence in the good execution. But still, when you want to use it, you still have to dig into, I mean, some low-level details in terms of how to implement a controller, and that can be quite complex. So we came up with at Tecnalia with a model that enables to implement different controllers, but focusing on the task that we want to regulate. Because in many cases, when we control a robot, we want to regulate a task. And the advantage of the mechanism that we propose is that the developer here just focus on the task, and all the plumbing required to be compliant with the ROS control interface to connect it to the real system is automatically generated. So that if we take a simple example where we want to make a peg in a hole experiment, well, the controller description is likely to be as simple as what you can see here. Of course, we have to define where is the peg, where is the hole. So we have a simple methodology to define the location of the different frames in the environment and with respect to the robotic arm. And then we just specify that we want to use a servering control to bring one frame inside another at the location of another frame, which is what you can see on this simple example. And that's the type of control scheme that we have been using to define the different controllers that you have seen today, like the one for inserting the tube. That is exactly the same controller we also use to make the same operation, but with the dexterous gripper out CEA. Of course, some key control points are slightly different, but the controller we use is exactly the same in terms of implementation, as you can see here. And what is interesting with that system is that you can as we focus on the task level, and that's my almost last slide, is that it's quite practical to define the control that you want to implement. Like for example, in that example, no, I should not. Should do that first. Here you have a mobile camera that is looking on one gripper that is looking at the other gripper. And so what we are going to ask him is to keep this gripper focused into the image. And that's what you can see here. It's not synchronized, but you get the principle out of it. And here we are just defining the motion of this left gripper, that is go and grasp the canister, insert it into the tray. And the control of the other arm, if you try to define it from the outside, it can be quite complex. But at the end, it's pretty simple if we just say, no, I just want the second gripper to be focused and centered with respect to my camera. And this is super simple to express in terms of task if you focus on the frame. And doing so, we can have such type of advanced, following strategies that in task frame is quite simple to implement. And that is typically what we are using to implement, if I can switch here, a type of joint synchronized behavior that we are also using to implement the tube insertion, where here we are just asking the two gripper to stay at a given distance, one with respect to each other. So you see here that there is a lot of admittance. My colleague Miguel can very easily move the different arm, and then just can control one of the two arms, and they will maintain a constant distance in between the two, still be compliant to a motion in the vertical axis. But in that case, we have a pretty, easier control of the motion of the two robotic system. And this is typically the context that we were using to enable the insertion of the tube inside the holder. So this, just to say that this control framework is quite efficient for developing different types of controls. And just to sum up on this part, so there is different level where we can simplify and help in the definition of the in the programming of the system. At a highest level, it's quite important to have some abstraction because it is the implementation, the collaboration, and the extension of concept. Regarding the programming interface, the grounding with the ontology is super interesting because it enables to simplify also the teaching that we perform there. And at the low-level control that I ended with, well, the constraint-based modeling that we propose greatly simplify the programming of quite complex control modalities, and the compatibilities with ROS is also enabled to apply it to different platforms. And with this, I will end up my presentation more or less on time, well, few minutes late. Thank you for your attention. I don't know if there is one